the sediment which is delivered in a basin, because this is another aspect. So when we talk about a basin, so there is a provenance, there is transport, and then finally it reaches the basin. Right? So today our main topic will be how the sediment that reaches to the basin. What we already discussed is its subsidence history and how the basin behaves. The basin, it behaves either for tectonic reason, for the thermal reason, or for the water load and the sediment load. That the entire basin, how it behaves. Now today our discussion will be mainly how the sediment it reaches to the basin and how it is generated and reaches to the basin, what load of sediment that comes to the basin, what is the role of climate in that, what is the role of lithology in that, and what is the role of the chemical, physical, and biological processes of weathering within this entire history of the sediment generation that is reaching into the basin. So today our discussion, it will be basically the mechanical, chemical, and biological generation of sediment and its reaching out to the basin, reaching out to the basin. That we are basically discussing. Now, any sediment that reaches a sedimentary basin, where from it comes? It comes from land, because all the sediment that is being generated from the land by means of different erosion and weathering. Even if you think of the generation of carbonates and evaporites, all these things in the marine basin, suppose carbonate, then again the productivity of carbonate, productivity of organism, that also dependent upon the nutrients that will be delivered from the land by means of weathering and erosion. So what we actually get, that it is not only the sediment in form of a particulate matter, in form of a terrigenous sediment, in form of a plastic sediment, it is reaching out. But there are a large amount of sediment which comes in the form of suspension, it comes in the form of dissolution in the water column. So all these that basically comes to the basin. That not only this sediment, they themselves are responsible for the filling, but they are also responsible for those sediment which generate within the basin. Suppose a carbonate, its productivity is completely dependent upon the nutrients supplied by the weathering and the erosion of the land surface. Now this entire synchronity of the system, that is the weathering and erosion, that again dependent heavily on the climate. It depends upon the climate. So what it depends upon the climate? Depends upon temperature, depends upon precipitation, and depends upon evaporation. All these factors, they are equally important, that how much sediment that will be delivered in the basin. What is the catchment area? What is the drainage area? What is the area from which is supplying the sediment? How much is the potential of that area to supply the sediment? All these are dependent upon that what is the climate in this region, what is the lithology of that terrain, what is the precipitation amount, what is the temperature of that area, what is the evaporation of that. All these together, that basically controls that what is the amount of sediment that will be delivered in the basin. Okay. Now, if I can think of, so what really we are talking about. This you from your very first year of the UG geology, you are listening to the term erosion and weathering. Now, what is the difference between erosion and weathering? Erosion is mostly a mechanical process, whereas weathering, which erosion is also been referred in the term of physical weathering. So, when we refer to a physical weathering and erosion, there is hardly any difference between physical weathering and the erosion, because erosion itself is a physical process. It is a mechanical process. When we really talk about weathering, we actually talk about chemical weathering. So what is chemical weathering? The chemical weathering, it is the transformation of the minerals, transformation of the unstable minerals into a neoformed mineral. Neoformed mineral, and most of the neoformed mineral, they are clays. This we have discussed through your entire BSc and MSc of geology. Several teachers must have discussed that it is actually the chemical weathering which is responsible for the change of the mineral from. Now, so what it actually does, that this chemical weathering, it transforms the rock into soil. It transforms the rock into the soil. Now, this change of the rock into the soil, that pedogenesis, what we call the pedogenesis, this pedogenesis is one of the major role player in the chemical weathering process, and to generate the suspension load into the river system or the surface flow or the groundwater or the surface runoff, the generation of the suspension load as well as the solute which get dissolved, the cations and the anions that get dissolved in the water column. So all these are the process of the pedogenesis. Now, if I consider the three different kind of system, one is the tropical unit. Tropical unit. Another is temperate. Last is arid, semi-arid. Now, please draw this figure, then I am discussing. You can see the figure?
Yes, sir.
Okay. Is it done? Mistakenly, I opted for exit from the WhatsApp group. Hello. Can you hear me?
Yes, sir.
Yeah, actually there were three groups in the name of sequence stratigraphy, which were earlier years also. So I was exiting from that group who have passed out. So in that process, I also made the exit from your group. So please add me in the group, because there will be many things coming. The exams will be coming, so a lot of instructions has to be given. So please include me in that WhatsApp group also.
Okay, sir. So Kriti is admin, so we'll tell her to add you.
Okay. Because
Okay.
there were 3, 4, so all the names were sequence stratigraphy. So I was totally confused.
Okay, sir.
You have drawn it.
So what is written in the last column?
Silkcrete, gypcrete. Silkcrete, gypcrete.
Okay, sir. Done.
Okay. So here there are 3 columns. They are representing 3 different climatic zones. Considering the same bed load. Suppose the bed load is a bedrock. Considering the same bedrock, suppose it is a granitic or gneissic bedrock. And I am putting that granitic or gneissic bedrock into the 3 different climatic zones. How the 3 different climatic zones they will behave in their action. When you have a tropical humid zone, you have a very deep rooted soil zone. You have a very deep rooted soil zone, and most of the unstable minerals such as hornblende, pyroxene, biotite, feldspar, all these unstable minerals, they get changed. They get changed. Okay? And they get changed to the new minerals, that the different kind of clay minerals, kaolinite, illite, smectite, chlorite, all these different kinds of new mineral, that is the clay mineral, they get formed. In a very extreme case of this entire process of changing over, of the original unstable grain into the stable grain. This is what we call the process of pedogenesis. We call it the process of pedogenesis. Process of pedogenesis. Now this pedogenesis, that is very deep rooted, and you are getting the all the unstable minerals, they are changing to the neo mineral, that is the clay minerals. In some extreme cases of pedogenesis, you may get the formation of bauxite or laterite in this zone. Bauxite or laterite in this zone, where you either have a high degree concentration of aluminium or high degree of concentration of Fe3 plus. Fe3 plus, then the laterite, or aluminium concentration, then you got the bauxite. Now you come onto the temperate zone. Here the soil formation is not so advanced. You get soil in the top part where the soil pedogenesis. Then you have a very well defined zone which separates the soil from the bedrock. That zone, what we refer to as the saprolite zone, where the bedrock has not fully changed into soil, but is in the process of changing to soil. So, what is the character of the saprolite? The saprolite, there will be the large blocky bedrocks. These are all bedrocks, and they are fractured. So you have the water movement in that, and the bedrocks are fractured. So that is the character of the saprolite, and where the bedrocks are intermediately changed. They are in the process of changing. That is called the saprolite, where you get the extensive carbonate dissolution, water percolation downward, and there you get the neomorphic mineral, the neomineral clay only in the topmost part. Now you come to the arid zone. Here the minimum of the soil formation, very thin soil layer, because the unavailability of water, and the bedrock you can get even up to here. But here, because wherever there is evaporation, that will exceed the precipitation. Evaporation exceed the precipitation. There you will get the formation of silkrete and the zinc. Okay, fine. So this is the fundamental difference with the same bedrock in three different kind of climatic zones. What will be the effect of the climate on that particular bedrock to generate the different kinds of. So if I summarize this, So all the three different kind of cases, what I have just discussed, then what kind of yield they will give, what kind of yield, what kind of material they will supply in the stream. Because what happens really, so please draw this also. Is it done?
Yes, sir.
Okay. So what I am trying to say here, and that is very clearly depicted possibly in the diagram, that you have the generation of the saprolite soil, and this is the entire profile. And in the process of this pedogenesis, you are basically not only releasing the bed load, but also you are releasing the solute as well as the suspension. So all these, they are either by surface runoff or by groundwater flow or by different kinds of mass wasting process related to the glacial action, the wind action. So all these are the processes of sediment transport. So you can have this movement of the solute and the suspension load in terms of the surface runoff, the groundwater flow, mass wasting processes, that is the different by the ice or the wind, that all these processes, they basically deliver the sediment into the river system, which finally reaches to the ocean system. So that now this entire zone, now this zone of the soil formation and sediment delivery, which is the main zone, is this in the humid climate, is this in the temperate climate, or it is in the arid climate? In which climate it is? And depending on that, what kind of material it will supply into the river system? What kind of material? Or every time they will supply the same material? No. When you have a humid tropical, then your supply will be mostly neomineral, mostly the clay. They will be supplied, the clays will be supplied with some amount of quartz, and the cation and anion, you have the sodium, potassium, calcium, bicarbonate, chloride. So all these, they will be more supplied when you have a humid tropical climate. And there, now you have a temperate climate where some amount of neomineral, but along with that you also have some kind of quartz and mica. So the contribution of neomineral and quartz mica, it may be around 60:40. Whereas here the clay with the quartz, this will be about 80:20. 80 will be the neomorphic clay mineral and 20 will be the quartz. But here you will see the neomineral, it may be 50 to 60%, and the quartz mica will be 40-45%. Now you come to arid, where you do not have much of the neomineral. You essentially quartz mica rock fragment, they will be more supplied. You hardly get any clay. The clay will not be supplied, and very low amount of solute. Very low amount of solute. So all these, because the calcium carbonate goes into solution, so you get the more of calcium here also. So my aim here is to discuss with you that depending on the this climatic zone and the precipitation, the evaporation, the temperature, all these factors together, we basically get that what kind of yield I will get in the river system, and that river system will finally divulge its load into the ocean system. So what kind of any river which is a more sandy river, a river which may be more clay or muddy river, a river which may be a mixed load river. So a mixed load. So this river system which is draining, it will be more muddy river. This draining, this will be more mixed load, and this will be more sandy rivers. So though the total river character, the load of the river, that gets changed, and as the load gets changed, the river geometry gets changed, river anatomy gets changed, and the entire river that takes a different shape. So if you have a more mud-rich river, there will be more stabilized channel, there will be more the more aggradation of the system, you get more of the floodplain, more of the levee. But when you have a sandy, there are more mobile channel, there will be more the channel will not be very stagnant, and they will be very quickly moving from one side to another. So the kind of delta that will be formed, the kind of the sediment it will supply into the ocean basin, everything will get deeper. Everything deeper. So you can, my message here is that how the land and its weathering pattern. It is changing the river pattern, its river bed load, river solute content, everything, and finally the sedimentation pattern that it will into the marine basin. So that is the main goal that I was trying to tell you. Is it okay, or there is anything what needs to be discussed? Is it okay?
Yes, sir.
Okay. Now, once so what we basically is discussing that the pedogenesis plays a very major role, and that pedogenesis, that the soil formation that is of different type. As you know, because we have a faculty in our department who actually works on the soil, and he is very knowledgeable on the soil. I am not very conversant. Professor Srivastava must have discussed with you a lot about the pedogenesis. Am I correct?
Yes, sir.
Yeah. So you people may be knowing more than me about the pedogenesis, but I just want to discuss it in an aspect of pedogenesis, not going into the detail of the pedogenesis. As you know, that any pedogenesis, it depends upon the precipitation and evaporation. That how much there is precipitation and how much there is evaporation. So the precipitation, evaporation, then temperature, all these factors. That now if you have a humid tropical where you have the precipitation overtakes the evaporation, then what will happen? That if precipitation overtakes the evaporation, and then you have the water that will percolate down into the water table from the soil formation, that is the pedogenetics phase. The water percolate down to the, and with this the organic matter also percolate down. Organic matter.
All my appreciation.
Organic matter also percolate down. Okay. Now this organic matter and percolate down, they do not change very readily. They do not change very readily. Now, when they do not change very readily, then you get a gray soil at the top, and the iron do not get much of oxidized. So you get a gray soil in the top. Am I clear what I am trying to say? If you have a condition where precipitation exceeds the evaporation, now precipitation exceeds the evaporation, what will happen? The water will percolate down to the water table. Along with water, the organic matter will percolate down, and the surface soil, it will have a gray color. Okay, which is called the pet soil and clay soil. All these the two types of soil, that is the pet soil and clay soil, that you basically generate there. Now, if that you get the more what we call the changes, that the change is not very slow, change is becoming fast, then the kind of soil that gets changed, and the iron, it may also become +2 to +3, and then you get the coloration of the soil. So I am not going to the deep into it. You know all the different processes of the soil formation, and also you have the paleopedology, that the ancient succession where you get the formation of the soil. What I want to basically harp on here is that the two conditions which really do not allow the major soil formation. What are the two conditions? One is erosion, another is high sedimentation. Both the things, erosion and high sedimentation, both the things, they do not allow the mature soil profile generation. So for any mature soil profile generation, you have to have a steady state, and that steady state, that means the erosion, if I draw a diagram, then it may be more clear to you. If I draw a diagram, it may be more clear. Please draw it, and then I am explaining what I tried to say. Is this figure known to you? Is this figure known to you? Hello? Have you seen this figure related to pedogenesis before?
No, sir.
Okay. Because I don't want to repeat the thing. Is it done? Hello? Is it done?
Yes, sir.
Okay. Now, what I am trying to say here is that there are two things here you must remember, that where I should get a proper pedogenesis. Pedogenesis means the soil formation. And where I should get the soil formation, where I will not get the soil formation. This is suppose these diagrams, what it shows, that there is the suppose there is up to this is the active, I should say active level of pedogenesis. Fine. Now within this active level of pedogenesis, the soil formation that you get in this zone, the sedimentation rate SR is this. Okay. Now, what I am saying, that suppose I have a sedimentation rate which is 2000 millimeter per annum, and you have a rate of pedogenesis which is 2 meter. 2 meter pedogenesis with a sedimentation rate of 2000 millimeter per annum, you require about the residence time of 1000 mA. That means that a residence time of 1000 mA that can stabilize its equilibrium in the pedogenetic zone, the surface, and allow it for the over 1000-year time that it will be getting the soil profile of 2 meter with a 2000 millimeter per annum sedimentation rate, and that sedimentation rate you are allowing the residency or the retention of 1000 annum, then you get a 2 meter of soil formation. Are you getting my point, what I am saying?
Yes, sir.
Now that is represented. That is represented. Yeah. On one side you have the rate of sedimentation. So the rate of sedimentation that is increasing, and as your rate of sedimentation increasing, your chances of formation of soil is decreasing, because your surface will not get at the same equilibrium level of pedogenesis for a long period of time, so that the soil can form. Your surface will get buried, and you are not allowing your surface to remain in the soil formation zone for a long period of time. So as the rate of sedimentation, this is millimeter in annum, that is decreasing, your chances of soil formation is increasing. And then you can see that the curve is something like this, and then I have drawn a line on this side, there will be no soil. There will be no soil. Because you require not only low sedimentation but a long residence time for giving, you have to give for formation of the soil. Then, if as you increasing the time with low sedimentation, your soil that gets formed. And if you allow its time up to this is over matured soil. Over matured soil. So this is the minimum residence required. Minimum residence required for the, this is the minimum residence required for formation of any soil. Below this there is no soil. This is the minimum residence required for formation of any soil, and then you require timing for giving the overmatured soil. Am I clear? Yeah, in this in a rate of sedimentation and timing of pedogenesis curve, you have to understand that what is the importance of the rate of sedimentation and the residency.
Yes, sir.
Okay. Now if this concept now we apply in this zone, So this is a profile where you have a mechanical erosion at the top. Mechanical erosion. You have a soil. This is the soil saprolite transition. This is the saprolite. This is saprolite bedrock transition. And this is bedrock. Okay. Now this transition, I mark it that at what rate bedrock is changing to saprolite. At what rate the bedrock is changing to saprolite. So that may be a rate PR1. At what rate saprolite is changing to soil. That rate may be PR2. And what rate the mechanical erosion is taking place. That may be ER. You see, PR1, PR2, its rate, and what rate you are removing the soil, at what rate you are erosion. If you erode more rate than the rate at which soil is forming, then no soil profile will develop. You will not get any soil profile. If you allow your PR to exceed the mechanical erosion, then you get a soil profile preserved in area. I am showing it by a diagram. Please draw the other diagram. Where ER, rate of mechanical erosion, PR1, rate of bedrock saprolite transition, PR2 is rate of saprolite soil transition. Figure is fully visible to you?
Yes, sir.
Is it done?
So what is written below soil profile?
Soil profile, this one, soil profile foundation.
Okay, sir.
So what is shown in this figure? That there are two different transformation phases, that from the bedrock to saprolite, and that rate of change of from bedrock to saprolite, that we are assigning PR1. Then the saprolite is changing to soil, and the rate at which the saprolite is changing to soil, that we are getting PR2. Now, this is a in situ process. Now, if your removal rate of the soil, that is the physical erosion, is more than that, and which is represented by ER. Now, there is a balance. You need a balance between the ER and PR. If the PR exceeds ER, that means the amount by which you are doing the pedogenesis, the rate of removal of soil is not more than that, it is less than that, then you are preserving the soil and a soil profile will develop over the time. So 100 million year to 1000 million year, you get the development of a soil profile, because the soil which you are forming, you are not removing that quick. Now this is a steady state where the soil which is forming, that is getting removed. So soil is forming, so no soil is preserved in its original place. It is a steady state, that whatever amount of the soil that you are forming by chemical process, that is being removed by the mechanical process. But when your mechanical process overrides the soil formation process, then what you do? You actually cut across the entire profile and generate a slope, exposing the bedrock. When the soil profile, pedogenesis rate is overtaken by the mechanical erosion, then you do not get not only you do not get a soil profile, but you cut across the entire soil profile and expose the bedrock and the slope generated. Normally what we do, we call this kind of process. So, and then at the base of the slope, you generate the colluvia. At the base of the slope, you generate the colluvium. Okay, so what we call it? It is a weathering limited system. We call it weathering limited system. So in this system, actually transport is dominating. Weathering, you are limiting the weathering. So any weathering limited transport dominant system that will generate a kind of slope and that generates a steep gradient in the system. A steep gradient, there will be lot of mass flow, there will be lot of mass wasting process, and all these, suppose there is landslides, there are in the hilly regions. What is happening in the hilly regions where there is so much of landslide? It is basically a weathering limited system. But you are not allowing the weathering because you are regularly removing the weathering profile, forming the road, forming all the development, and then it becomes a transport dominant weathering limited system. And that kind of system will always lead to any kind of landslide, any kind of mass wasting, any kind of mass flow, and that will cause all the damage. Now, what will happen here? Here your mechanical weathering that is less than the chemical weathering. So the chemical weathering that is overtaken, so you get a good soil profile, and that good soil profile help in. So normally where you get the good soil profile? Where there is a very low gradient horizon, you do not get much of mass wasting process, and that is being maintained for a good retention time, or there you get the soil formation process. Am I clear? Is the thing is clear?
Yes, sir.
Yes, sir.
Okay. So now this what we will call it? We will call it the transport limited system. Transport limited system. Okay, fine. Now the question comes that when there is a soil profile development and there is formation of the load, then what will be how the different kind of system they will be responding to it? What is the role of lithology, and at what rate that lithology will be responding to this process? Responding to this process. Now, I have discussed the different effect. Now I am discussing the different kind of lithology. What is its role? Lithology, what is its role? It is in meter per annum. You can see that the dissolution rate is very high in the meter. So if you have a rock salt, it will be dissolved very quickly. In case of tropical, entire rock salt. Even in case of temperate, you get entire rock salt to get dissolved and go into the river water. So any rock salt, if it is present in the provenance, that will be very quickly dissolved, and it will provide all kinds of the sodium, potassium, calcium into the river system. So the dissolution capability of rock salt is very high. Then the gypsum, so it is basically the sulfate. So the sulfate, their dissolution is lesser than the chlorides. So the chlorides, they will go into dissolution fast. Then the sulfate, they will be going to dissolution because it is in the millimeter per annum, 200, 400, 600 millimeter per annum. And the sulfates, they will go into dissolution. Then comes the carbonate. If you have the carbonate, then you that will go to dissolution, and depending on the tropical area, you get the higher dissolution and relatively lower dissolution depending upon whether you are in a tropical or you are in a arid, semi-arid climate. If you have a large amount of, tell me one, you have drawn it. Have you drawn it?
Sir, drawing.
Okay.
Sir, done.
Yeah. So what we are showing here, that the different kind of material with their different rate of dissolution. Given the same condition, the different lithology, they will be responding differently. The one of the highest solution capability, that the first it will go into dissolution and it release its cations and anions in the river system, that is the rock salt. So if you dissolve the rock salt, you get the sodium, the potassium, the chloride, all these things they release in the water column of the river, which will be carried to the ocean. Okay. Now you get the gypsum, which is a sulfate salt. The sulfate salt is the next victim, and their dissolution rate is 200, 400, 600 millimeter per annum, and they will be released. So the calcium sulfate, so sulfate ions, they will come next. First chlorides will be released, then the sulfates will become. Sulfates, the calcium, and all these they will be released by this, and then comes the carbonate. Carbonate, depending on the tropical or the arid, you get the different dissolution of the carbonates, and the carbonates they get into the, so the calcium, the carbonate ions, anions, all these that will be released. Now you tell me what I was just asking, where I should expect. If I get in a sediment column, there are large amount of the detrital carbonate grain. Where I can expect the detrital carbonate grain? Carbonate, without going into dissolution, it is supplied in form of mechanical grain. Where I should expect? Can you tell me where I should expect? Normally, carbonate will go into dissolution. If you have, but in a sediment column, I am seeing that there is a carbonate which is supplied as a mechanical grain. I am getting a cross-stratified carbonate. How, in what kind of condition I should expect that? Carbonate plastics. Normally carbonate will go into dissolution. Carbonate plastics कब आएगा? Any idea? Is my question clear to you?
So when the provenance is carbonate,
So why carbonate has not gone into dissolution? Because the carbonate, as I am drawing this figure, the rock salt, gypsum, and then carbonate dissolution, that is the millimeter per annum. But if I find that carbonate is not going into dissolution but being supplied as a mechanical grain as a detrital grain, where it can be possible. Okay, I am telling you, it can be possible if you are actually in a arid climate, where you do not get the proper water for the dissolution of carbonate, or where the slope or the gradient of the provenance is very high, which actually forming a weathering limited system. You are generating a weathering limited system because of the gradient of the provenance. In that case, the carbonate will not go into dissolution, but it will be supplied as a mechanical grain. Because anywhere, if you do not give the weathering rate to proceed, am I clear what I am saying?
yes, sir.
So, got my point, what I am trying to say. It is not
Yes,
that
sir.
the carbonate will always go into dissolution. Carbonate can also be supplied as a mechanical grain, provided there is a arid climate and a high gradient and I am generating a weathering limited system. But if I consider that it is not a weathering limited system, I am giving it a proper weathering system and a pedogenesis system, then this is the scheme by which the different lithologies will respond. This is the scheme. And then the carbonates will be dissolving. And then you get the last what I have drawn, that is millimeter per annum, and you can see that the 2 to 4 to 6 is a very, very dissolution, very low. There is hardly any dissolution. There you get the basalt, granite, metamorphic rock, slate, quartzite, they respond like that. Okay? So now in the you see that in the granite you have feldspar. Feldspar will also decompose to clay. But their rate of decomposition is very, very low. Very, 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 very. Even in the Precambrian sediments, we get the preservation of feldspar. And there are large amount of feldspar presence even in the Precambrian. So you can see that more than 100 million years, the feldspar is still surviving. So that rate of change is very low. But you get the most of the cations and anions in the river system, they are there is a dominant supply from the rock salt, gypsum, carbonate, but of course there is supply also from the granite and here, but their rate of supply, you cannot compare these rates of the different lithologies. There is a huge difference in the rate by which they supply the cations and anions and the solutes in the system. Is it clear?
Yes, sir.
Okay, so let us stop here. So I think you are getting that what I am trying to say, because this will finally make the budget in a sedimentary basin. How you will get the total budget? Now this entire soil formation, what is happening? You are actually decreasing the topography of the land. What is called the denudation. You are actually doing the denudation, isn't it? You are lowering the level. You are weathering and transporting the sediment. By that means you are lowering the level of the land, which is called the denudation. This lowering of land, the rate of lowering of land, that you call the denudation. Now this denudation will basically supply the sediment in the form of plastic, sediment in the form of suspension, and the different thing into the water column. We will discuss the next class, but how this denudation that control the your plastic supply, your suspension supply, and what is the budgeting of that? What is the budgeting of that? Okay.
Okay, sir.
Thank you.
Thank you, sir.
Thank you, sir.